I'm Doug Fern, and this is my take on music recording. In the previous 2 episodes on magnetic tape recording, we looked at the principles and the routine maintenance required to make good-sounding recordings. Now we're ready to record some music. Our tape machine is properly aligned for the reel of tape we will use, and we put reference tones at the beginning of the tape. Those tones are used to assure that the playback matches our record, especially if the tape is subsequently used in another studio or a mastering facility. We decided to record at 15 inches per second, which is a good compromise of many variables. Our machine is a 24-track multitrack with 2-inch tape. If you have only used digital recording before this, you will find that the playback has a lot more noise than what you're used to. With digital, noise is a non-issue, and the recording level is relatively non-critical. As long as you never go above 0 dB full scale, you will have a usable track with low noise. Not so with tape, because each track in the mix will add its own noise. Tape is noisy, and you have to keep the levels up to maximize the signal-to-noise ratio. The good news is that going over 0 VU is not the end of the world, so you can keep the levels up much higher than you might with digital recording. A moderate overload on a tape track will change the sound somewhat, but it won't sound bad unless your level is significantly over 0 VU. Tape noise is most obvious in the higher frequencies, which is why it is called tape hiss. This was a major problem in the first decade of recording to tape, and as the track count went up, the problem got worse. Ray Dolby came up with a brilliant scheme to minimize tape noise, and his Dolby A noise reduction system became nearly universal in recording studios from the late 1960s and throughout the tape era. The Dolby system is simple in concept, but requires precision in the circuitry and, equally importantly, in the tape machine alignment to make it work transparently. Basically, the audio spectrum is divided into 4 bands, and each band has a compressor optimized for those frequencies. On playback, an expander circuit restores the audio to its proper dynamics. Critically, the Dolby A system only affected the lower-level audio. The moderate to high-level audio is not processed at all. The result is a stunning reduction in noise, with little or no impact on the sound. The exact amount of noise reduction is subjective, but it's at least 10 dB and probably more like 20 dB. When you consider that the noise level of a standard tape machine is only about 60 to 65 dB below the maximum level, that's pretty noisy. Compare that to most digital systems where the signal-to-noise ratio is often approaching or above 100 dB. And every time you add more tracks, you get more noise. The drawback to Dolby A noise reduction was that the machine had to be precisely aligned, or else the playback would not be accurately decoded. To make sure the overall level was correct, a distinctive tone, called a Dolby tone, was recorded at the beginning of the tape. This tone was used to calibrate the playback level. And the Dolby units were expensive, and you needed one for every track you used. A later system called Dolby SR is even more effective, bringing analog tape noise levels close to the noise level of a digital recording. But we will assume you're not using noise reduction, and you will live with the noise. With some types of music, tape hiss is not a big issue. At the beginning of your tape, you would have a Dolby tone, if necessary, followed by a 1 kHz and 10 kHz tone at 0 VU. The next thing you need to know is that tape should always be stored tails out. That just means that the tape is played all the way through, and the take-up reel on the right side is what you will put in the box for storage. There are several good reasons for doing this, but the main one is to have the tape wound under constant tension, which prevents damage to the edges of the tape during storage. Tails out means that you have to rewind the tape before use. Okay, we're ready to record. Remember the difference in setting levels between digital recording and tape. For tape, keep the recording level up. But also keep in mind the problems that can result from recording sounds with a lot of high-frequency content. Keep those levels down to the point where it sounds good on playback. There's also a different workflow with tape. For one thing, it takes time to rewind the tape. So if you're overdubbing and punching in, there will be a few seconds getting the tape back to the pre-roll point for the punch. This can be a good thing or a bad thing. Some performers want to get right back to recording before they lose their focus. Others welcome the short break to prepare themselves. And punching in is different too. With digital, you can be a bit sloppy with your punch, since the transition from playback to record is milliseconds at most. You can also undo your punch if it didn't work. With tape, there's a definite transition from play to record. The new material does not come in instantaneously, but rather takes a perceptible amount of time. This is due to the spacing between the erase and the record heads. There's a short time when the tape is erased but not yet recorded. This isn't a major problem because the time is short, maybe 100 milliseconds, but it does mean you have to slightly anticipate the punch. And, of course, the biggest difference is there's no undo on a tape machine. A punch that was ill-timed may be difficult to fix. So if you mess up on the timing, you might have to go back and find an earlier place to punch in. The first few generations of tape machines did not have locators, counters, or any way for you to know where you were in the song. With those machines, you had to rely on your experience of how long it took to rewind the tape to a precise point. And the time varied depending on where you were through the reel. During rewind or fast forward, modern machines have automatic tape lifters that pull the tape away from the heads. This is necessary for several reasons. First, it saves a lot of wear on the heads. And second, the level off the tape goes up with the tape speed, so during rewind or fast forward, your monitor level is going to skyrocket. This isn't good for your monitors, your hearing, or any mechanical meters. On those machines, you had to manually open the gate in front of the tape heads to get the tape away from the heads. Later machines did this automatically. In either case, even with a 1/4 inch or more away from the heads, you can still hear the audio at reduced level without highs, but of course with the pitch of everything significantly raised. With practice, you can actually count measures in rewind or fast forward, especially over short time periods in the song. But this will vary with the amount of tape on the reels, so it's a dynamic thing. You'll get a feel for it after a few sessions. But what if you recorded multiple takes, and now everyone wants to go back and hear take 3? How do you find that? Well, you might be able to count forward or back as the tape flies by, especially if you have some dead tape in between takes. But there's another way to do this, slating. Slating is analogous to the clapboard used in film, which is used to identify the take and provide a synchronizing signal to align the audio and visual elements. A slate on a tape machine is similar in that it provides an audible announcement of the song and take number recorded just before the performance begins. It's a great idea to help you keep track of where you are in a series of takes. Part of the slating process, available on many vintage consoles, is a simultaneous recording of a low-frequency tone during the vocal part of the slate. Generally, a 20 Hz tone will be recorded, which will be mostly inaudible at normal speed. But during fast forward or rewind, the tone would be shifted up well into the mid-range, and it would be easy to hear. You just had to count the number of beeps that went by to know where you were. More recent tape machines have counters that kept track of where you were in the tape. These have to be set at 0 at some easily identified point on the tape, typically just after the reference tones. The accuracy of the timer would drift over a session, so it might become necessary to reset the 0 point several times over the course of a session. Machines also had memory locations starting in the late 1970s. This made it possible to keep a log of important points in the song, just like we use markers in digital recording. But of course, these location points tend to drift during a session, so you periodically have to reset it. There's one other thing you can do with tape I should mention, and that's variable speed. This was used extensively in the 1960s and even the decades before and after. If you listen to any of the Beatles recordings, almost all those vocals were recorded at a slightly different speed than the rest of the instruments. You do this by slowing down the tape, typically, so that when the singer sings along with it, they have to sing it at a slightly lower pitch. When you bring it back up to normal speed, the pitch is correct, but the vocal takes on a different quality. Taken to an extreme, this could sound like the Chipmunks. When done minimally, it adds a subtle change to the quality of the vocal. Another application of variable speed is if you have to later overdub something that's fixed tune like a piano on a track that wasn't recorded with great accuracy in the tuning. You can change the speed of the tape to match the pitch of the piano. In the era of synchronous capstan motors, this was pretty tricky to do because you needed to run an oscillator through a really high-powered amplifier that could drive the capstan motor. You then vary the speed by changing the oscillator above or below 60 Hertz. Later machines had variable speed built in. This is a very useful technique and something we've lost in the digital age because doing this in the digital domain is not nearly as simple. Remember, this is different than auto-tuning or correcting a pitch. The speed change is pretty minor, generally much less than 2%, so the effect is pretty subtle. Okay, we have a few tracks recorded and everyone is happy with how it sounds. Now it's time to overdub some new tracks. This works a little differently than it does with a digital workstation. For one thing, there is much too much delay between the record and playback heads to allow us to monitor the normal playback for overdubbing. We have to monitor off the record head instead, temporarily using it as a playback head. There will be controls on the tape machine to enable this feature, and on later machines on a remote control. You're probably beginning to see why many studios used a tape op to handle all this. Often the tape machines were in a separate room to minimize the distracting mechanical noise of the machine. To overdub, we have to place all the previously recorded tracks in this sync mode. Now our new recording will be in time with the previous tracks. Works fine, but it requires a lot of switching back and forth between normal playback and the sync mode. Later machines handled this with some level of automation, but you still had to pay attention to the mode a track was in. The earliest multi-track tape machines had 3 or 4 tracks, which allowed a small amount of overdubbing. Then 8-track machines became common. 8-track recording is somewhat awkward, in my opinion. You have enough tracks to record several instruments on separate tracks, and still have some left for overdubs, but rarely enough to put every instrument on a separate track, and rarely enough tracks to do much overdubbing. But it was possible to mix some of the tracks together and put them on a new track on the same tape. This is called bouncing, and it is a different concept from what many digital audio workstations call bouncing. But let's think about this procedure. We are committing to the submix when we create the new track, because we are going to erase the original tracks and put new things there. So we have to have a vision of the completed song in mind before we do the bounce. because there's no way to change the balance later. It's kind of liberating in a way because it forces you to make mixing decisions along the way. Another problem with bouncing is that we have to use the sync output of the tape tracks we are combining. Although the quality of the reproduction isn't terrible from the record head, it's never as good as the normal playback. So we have to accept some loss in quality in our bounce tracks, mainly a loss of highs and some increased distortion. Also, we are making a copy of our original tracks, and unlike digital, each generation of tape that the audio goes through increases the noise and exaggerates any distortion. If that wasn't bad enough, there is another serious limitation to the bouncing procedure. You cannot bounce to an adjacent track. In other words, if you want to take tracks 1 through 6 and bounce them down to one mono track, you cannot go to track 7. You have to go to track 8. Not a big issue in that example, but what if the tracks you want to bounce are on 1, 3, 5, and 7? You're stuck. Can't be done. You have to plan this in advance to avoid backing yourself into a corner. But why can't you bounce to an adjacent track? It's because the audio and bias level going into the record head is pretty high, and it's not perfectly focused on the track you are recording. Some of the energy sprays out enough to get into the tracks on either side of the track we are recording. This occurs entirely in the tape head. It doesn't really affect the tape. But this kind of feedback occurs mostly at high audio frequencies. So your newly recorded track will feed back into the tracks nearby that are playing back. At the least, this will add some unwanted and generally unpleasant high frequencies into your new combined track. In the worst case, the system can go into feedback. So bouncing requires a lot of planning to work properly, especially when you're doing stuff with just 8 tracks. Machines with more than 8 tracks make this less of an issue, but you still have to accept some loss of quality in your bounced tracks. At some point, you're probably going to cut and splice your tape. This may be a simple process like sequencing the songs for an album, or a more challenging task of editing within a song. Either case will require some basic editing tools: a splicing block, a grease pencil for marking the point on the tape, a new razor blade, and splicing tape. Here's a brief overview of the process, but keep in mind there are many more details and nuances you'll need to research or discover by trial and error. To illustrate, we'll first presume you are splicing 1/4-inch tape. To practice, start out with a copy of your tape. Don't use the master until you've figured this out. The splicing block holds the tape securely for cutting and applying the splicing tape. It should be bolted down so it is solid and cannot move. You find the point for the cut by playing the tape normally until you are at the proper point for your cut. But the tape is going by at 15 inches per second, so you'll need to find the exact point by zeroing in by manually turning the reels by hand back and forth while listening. Of course, you are moving the tape very slowly, so it sounds completely different. Sounds with a lot of high frequencies like a snare or hi-hat are much easier to recognize than a bass note. When you are sure you have found the right spot, mark the back of the tape with your grease pencil. This has to be right over the gap in the playback head. That's the center of the head. Double check by playing the tape again and finding the spot again, without looking at your marks. If there's any doubt in your mind that you found the right spot, keep checking it because you don't want to make a mistake. Once you're sure you have it right, take the tape out of the normal path and put it into the splicing block. Center your mark on the diagonal slot in the splicing block. Don't use the 90-degree cut because it will cause problems. It could be audible when played and the splice may come apart more easily. Now cut the tape with a definitive swipe of your razor blade. Do not try to saw your way through the tape. Quick and painless works best with minimal trauma to the tape. and use a brand new single-edge razor blade. You can probably get a few cuts out of each blade, but by then it will get too dull for a clean cut. Use any other cutting tool at your own risk. I won't go into why, just take my word for it. Repeat the procedure for the other side of the edit. Then place both tape ends into the splicing block perfectly together with no gap or overlap. Use only real splicing tape. Believe me, you can't use anything else or you'll later regret it. Splicing tape is made slightly narrower than the tape to be spliced. So when you apply it to the tape, you have to center it so there's no splicing tape falling off the edge of the tape. How long should the splicing tape be? Well, for 1/4-inch tape, I find that about 1 inch works well. To further reduce the discontinuity of the tape at the splice point, I cut the splicing tape at an angle. This may not be necessary, but it works for me. Use your finger to press the splicing tape onto the tape. It will change color slightly when it is properly attached to the tape. Now we have to remove our spliced tape from the block. Do not peel the tape out of the splicing block. It's machined in a way to hold the tape securely, and peeling it out is going to damage the edges of the tape. The right way to remove the tape is by grasping the tape on either side of the block and snapping it out gently. Now thread the tape back up and play your edit. Not quite right? Well, now you have to determine the problem and do what needs to be done to make it right. I won't go into the details, but just be aware that you might have to put the original splice back together, or try something else. And keep track of all your pieces of tape. You might need them. And make sure you know which direction they go. For wider tape, the process is similar, but potentially even more nerve-wracking. Rather than editing within a song, more commonly you'll be splicing in a length of leader tape. Leader tape is used between tracks of an album to identify the chosen track on the multitrack or to separate alignment tones from the music recording. Adding leader tape is much simpler than editing music, but you still have to use the same steps. Leader tape is available for all tape widths, and it comes in either plastic or paper. Why would you use paper? Well, under many conditions, the plastic leader tape picks up a static electricity charge, which can cause pops and crackles as it passes over the heads. The crackling problem will not be an issue except when tape playback will require playing through the leader, such as when mastering an album. And most disc mastering lathes use the leader to tell the cutting head to advance to create the bands on the LP. Makes digital editing seem easy, doesn't it? Maybe your recording workflow allows you to do the editing in the digital domain. I'm all for that. I've done a lot of nerve-wracking editing on masters during the tape era and got paid very well to do it, but I have no desire to go back to that. Digital is so much easier. It's like a different world entirely. What else can go wrong in the world of tape? Up until now, we have assumed that our tape machine was in perfect condition, and our tape was perfectly manufactured. But what if the tape has a problem? This is more than theoretical, because all tape manufacturers had periodic problems. Making magnetic tape is extremely difficult, and sometimes things go wrong in the manufacturing process. The classic problem is tape oxide shedding. All manufacturers experience this from time to time. I won't go into the causes, but be aware that any reel of tape, new or old, may be or become unusable. Unfortunately, this is often not immediately obvious, since most effective tape is fine at first. But due to manufacturing problems, the binders that keep the oxide attached to the plastic tape can quickly degrade. And when this happens, the oxide begins to come off the tape. Slowly at first, you might notice that you have to clean the tape path more often than usual. Each time the tape is run, it loses a bit more oxide. On a complex project with a lot of tracks and a lot of overdubbing and punching in, the number of passes quickly builds up into the hundreds. Aside from the cleaning problem, you will eventually notice that the level on the tape decreases and the high frequencies start to disappear. What do you do if you encounter this on an important project? The only thing you can do is copy the tape to a new reel as early as possible and complete the project using the copy. Make sure the new tape is from a different batch, although this is no guarantee. When manufacturers had this problem, it could affect weeks of production before the problem became evident. Transferring the recording to a new reel presumes you have two tape machines with the same configuration. A 24-track tape machine cost well over $50,000 back in the 1980s. That's about $138,000 in today's dollars. Add Dolby noise reduction, and the cost is over $200,000 in today's dollars. Many studios could not afford this unless they had multiple studios. This makes digital problems seem pretty trivial, doesn't it? Another similar problem occurs even with perfect tape. Over time, some of the chemicals used in the tape evaporate, leaving the tape with poor oxide binding. Same problem, just one occurs years later. And it doesn't depend on the number of passes. This happens in storage as well. This has impacted many, if not most, of the classic recordings from the 1970s and 1980s. There is a partial solution to this problem, which requires baking the tape at a low temperature for a period of time. This allows the tape to be played once or twice. The audio is transferred to a digital format and salvaged. The bottom line on this is the tape is not archival. All recordings, even those made on perfect tape, stored under perfect conditions, will gradually deteriorate. The magnetic information lasts a long time, but not forever. Our musical heritage on tape is gradually floating away. Some studies suggest that tape starts losing quality after about 10 years. This makes archiving of irreplaceable recordings a high priority. I know I'm making the tape recording process sound really grim, but that's not my intention. Tape does have a lot of problems, but if you're willing to deal with these things, tape has a unique sound, and you can capture some of that pre-digital musical magic if you want to. It's a lot of work, and it will require you to learn new skills and practice them for a while before you get good at it. But if you are up to the challenge, there are plenty of good, used tape machines available. And with some work, you can restore them to their original condition. And quality tape is still being made by a few specialist manufacturers. We are past the days of routine recording to tape, and I don't miss it. I prefer the performance and convenience of high-resolution digital recording. But I still have my Studer A810 2-track machine, and although it needs some work to be functional, I want to keep it, if for no other reason than just to look at the beauty and elegance of it. One last thing, you still may be recording to a magnetic medium and not know it. If you use a hard disk drive, you are recording magnetically. It's digital, of course, and incapable of recording analog signals like tape does. But I think the days of magnetic disk drives are numbered too, as more of our drives are solid state. Technology moves on. This is my take on music recording. I'm Doug Fern. See you next time.